Here we are in section 23.3 where we are going to discuss similarity. College Board is fond of similarity. In fact, similarity falls under the broader heading of proportionality, ratios, rates, which is extremely commonly tested on the SAT in various contexts in terms of slopes and linear functions, this stuff here in terms of similarity. So you will encounter questions on similarity and proportionality in triangles and other polygons. When two figures are similar, the basic, very basic way to think about similarity is that two shapes or two figures have the same shape, but not necessarily the same size or orientation. So I'm going to go ahead and highlight that here. Same shape, not necessarily the same size or orientation. So you can see in these three pairs of figures on the left here, you've got two parallelograms here that are seemingly the same exact parallelogram in terms of their shape, but they do have different sizes. These two arrows have different sizes and different orientations, but again, they're same shape. You also should notice that, you know, their angles seem to be the same. This small acute angle here, this acute angle here. You've got a bunch of right angles here and here. You've got those right angles over here. These two M's or W's, if you are looking to go to the University of Wisconsin, then let's make those W's. And then over here, you've got two triangles that clearly are not the same shape. This triangle on the left, in fact, looks like it is a right triangle. That looks like a right angle there. There are no angles in this triangle on the right that appear to be right angles. So these two triangles over here are not similar. But again, the three pairs of shapes on the left here, one pair, two pair, three pair, those are similar shapes. In terms of polygons, let's talk about the two things that must be true in order to prove or to determine similarity in polygons. The first of those two items is that all corresponding angles are congruent. And again, we saw that with these arrowheads up here. We can see with this parallelogram that, you know, these two acute angles that correspond to each other, let's say those are the top right angles, the bottom left angles there correspond to each other. They look congruent. This top left obtuse angle corresponds to this top left obtuse angle, and of course bottom right. But all of those corresponding angles are congruent. Yes, the shape on the right, the parallelogram on the right, is smaller, but all of the angles are congruent. And then number two, all ratios of corresponding lengths are equal. And this is the proportionality. I'm going to write that over here. Proportional. Let's write proportional. All ratios of corresponding lengths are equal. So, for instance, if I were to establish that this side here were 6 and this side here were 2, and it should be pretty clear that those bottom sides of this parallelogram correspond to each other. So I would know that there's a 3-to-1 ratio in those two corresponding lengths, which means that all corresponding lengths, if these two shapes were indeed similar, all corresponding lengths would have that 3-to-1 relationship. So if I knew that this slanting side here were 3, I would know that the corresponding slanting side in the small figure had to be 1. Those two items are always true when polygons are similar, and if those items are true, then the polygons are similar. In example 5, what we're going to run through are a few instances where we have to determine similarity. In other words, we're not going to really be doing any math here. We're not going to be calculating side lengths. We're just going to be looking at a bunch of figures and determining whether any of the polygons, triangles, we've got some trapezoids in example B there, any of these polygons are similar to each other, and we're going to have to state a reason why, which we can do just by marking up the figures in some cases. So In example, obviously, if you want to try this on your own, go ahead and do so. You might want to write lightly just in case you need to erase when you watch what I do. In each example below, write which polygons, if any, are similar. This is the similar symbol here, this little squiggly here. We're going to write which polygons are similar and why they are similar. If there's not enough information to determine any similarity, we're going to write not enough info. So in example 5a here, what we should notice is that in triangle ABE and triangle ACD, they share one angle here. So I'm going to mark that angle with this little sort of arc looking thing. And we can see that they share another angle here. I'll just sort of bold over this 90-degree angle. So they have this angle here and the 90-degree angle here in common. Some of you may have learned something called the no choice theorem in geometry. And what that's all about is that if two triangles share two angles that are congruent to each other, then there's no choice but for the third angle to also be congruent. And you can do that if you understand that intuitively, great. You can also do it by throwing in numbers. You know, if we say that this angle here is 20, well, then the remaining angle in triangle ABE would have to be 70, and the remaining angle in triangle ACD would have to be 70. So again, those two angles, angle B and angle C, they must be equal to each other. And therefore we have similar triangles. We know that triangle ABE is similar to triangle ACD. Now, the order in which we write these three letters, these three vertices, those are angle vertices, we are going to write those in a specific order because we need to make sure when we write that two polygons are similar, we need to make sure that the order reflects the parts that are congruent or that are proportional to each other. In this case, angle A in one triangle equals angle A in the other. Angle B in the small triangle equals angle C. So we can see that B and C are matching up. They are the second or middle letter here. And then angle E and D, they match up. Those are the 90-degree angles. We could have also written triangle, you know, if we had written BAE, we would have to write that that is similar to triangle CAD. BAECAD. So the order in which we write these will matter. Obviously, the day of the test, you may not have to worry about how you write the order of these letters, but College Board certainly will. And you should know that if College Board tells you that BAE is similar to CAD, then they are telling you that B and C correspond, A and A obviously correspond, and E and D correspond to each other. So again, the reason that we know that these two triangles are similar is because all of the angles are equal to each other. And by the way, when we talked about these two musts up here, it is true that if this first thing is true, if all corresponding angles are congruent, then the ratios of corresponding sides will be equal in similar triangles. So again, if we knew that, I don't know, AE were 2 and AD were 5, then all of the corresponding lengths would have this 2:5 ratio. In example B, so we are told that AF, BE, and CD. So that's AF, BE, CD. Okay, so all these horizontal segments here, they are all parallel. Well, remember earlier we did talk about parallel lines, and we talked about same side interior and alternate interior, and in other words, all the angles that are and are not necessarily equal when it comes to parallel lines cut by a transversal. And you should hopefully be able to see here that when we have a trapezoid, let's say we've got this trapezoid, I'll just draw a separate one. Basically what's happening is you do have these two non-parallel sides that are transversals cutting through a pair of parallel sides. So in the same way that we did all that big small work to identify big and small angles, for instance, there's a big, there's a big, there's a small, there's a small, there's a small, there's a small, there's a big, there's a big, we can determine, for instance, in this figure, that since this is a small angle here and this is a small angle here, just like this angle here and this angle here, that those two angles are equal. So instead of writing an S, I'm going to write this and this. I have this angle down here that's going to be equal to this angle here. Similarly, up here, I'm going to do a 3 here and a 3 here. And that would be what? That would be this angle here and this angle here. Those are both big angles, okay? Big angles. So obviously in this figure we have a third parallel line. So I'm talking about this angle here is like that angle there and that angle there. Those are both big angles and therefore they're equal to each other. And then this guy over here, this is going to get messy, but I'm going to draw 4 of those. That's a lot of those little arcs. So what we have here is we have A, B, E, F. We have A, C, D, F, and then we also have the little trapezoid on top, B, C, D, E. So we actually have 3 similar trapezoids here. So again, what we have is we have A, B, E, F, similar to A, C, D, F, similar to B, C, D, E. So again, that's the bottom trapezoid, A, B, E, F. It's the big trapezoid, A, C, D, F, and it's the little trapezoid on top, B, C, D, E. They are all similar to each other because they have congruent corresponding angles, and therefore the side lengths will be proportional in this case. In example C, this is probably the toughest one of the bunch. For those of you that remember everything you learned in geometry and really enjoyed geometry and maybe got solid A's across the board in your geometry class, you may remember some theorems about a right triangle that is split into some other triangles. So this was a right triangle up here, and then we are splitting that right triangle into a few other triangles by dropping an altitude. And you may remember some of those theorems related to such a situation and the fact that you're actually forming some similar triangles. Let's take a look at what they are. But the way that we're going to do this is we're going to do this with numbers, just so that we can see what's going on here. And I'm just going to pick some random numbers here. I'm going to make this angle here 50. I know that this is a right angle here because I've got a right angle over here to the right, and the two angles have to make up that 180 degrees in that line. And if this is 50 over here, this little angle up here must be 40. I also know that in this big right triangle where I have a right angle up here, I have a 50-degree angle down here. Well, that means that this remaining angle in triangle DAB, so angle B, must be 40, right? I'd have a 50 there, a 90 there, and a 40 there. And now in this triangle ACB, I have a 90 here, a 40 here, so there must be a 50 here. I could also have determined that because, again, there's a 90-degree angle up here. I already have 40 degrees here. I would need the remaining 50 degrees there. So now step back and look at what we have. We actually have 3 right triangles here, all of which are made up of one 40-degree angle, one 50-degree angle, and one 90-degree angle. So I actually have 3 similar triangles, and the way this is going to go is I have triangle, let's do DCA. That's the small triangle here on the left with a 40, 50, and a 90. That DCA is going to be similar to, remember, D is the 50-degree angle. Let's do this medium triangle over here. So that's going to be triangle A, that's the 50-degree angle. C was the 90-degree angle in the small triangle. So the 90-degree angle in this medium triangle is also the C. So that's A, C, B. So again, D was the 50 degree, C was the 90, A was the 40. Same thing over here, 50, 90, 40 in that medium triangle. And then the big triangle, the 50-degree angle is D again. The 90-degree angle in the big triangle is actually going to be A, and the 40-degree angle is going to be B. So DCA, ACB, DAB, and I forgot my triangle symbols, but that's okay. Those 3 triangles are all similar to each other, and therefore we'll have many pairs of proportional sides. Down at the bottom in item D here, this one, while maybe not the toughest one of the bunch, is certainly the trickiest. So some students will look at this and right away they'll think that these 2 triangles are similar to each other. Why? Because they look similar. It looks like one is just a smaller version of the other. In fact, you do not have enough information, not enough info. I'll just write NEI there, not enough info. And the reason you don't have enough information is because all you know is that angle C in one triangle and angle C in the other are equal because they're vertical angles. But we know nothing about the measurements of A and B and D and E. How might we know that these two triangles are similar to each other? If we were told that AB is parallel to DE. If we were told that these two lines that contain segment AB and DE were parallel, well then, and we could use the Z method here, which I'll do in blue. Boom, boom, boom. So we would know that the angles in the crooks of the Z, this and this, so this angle up here and this angle there, they would be equal to each other, and therefore this third angle here and the third angle here must be equal to each other. But again, we are not told that AB is parallel to DE, and unless we were told that AB is parallel to DE, or we were given enough information to derive that or deduce that AB is parallel to DE, then we do not know that triangle ABC and triangle DCE are similar to each other. There is not enough information to determine similarity here. At the top of the next page, let's go ahead and talk a little bit more about those ratios and that proportionality in similar triangles. So again, if we are given two triangles that have three congruent angles, so I have angle X and angle X, obviously X is equal to X, Y equal to Y, Z equal to Z, but the triangle on the right is clearly larger than the triangle on the left. And keep in mind, we could also say that angle A is congruent to angle D, but again, since we have an X here and an X here, we know that A and D and X are sort of all equal to each other in terms of their angle measures. So for any pair of triangles like this, we know that our corresponding lengths are going to be proportional. Another way of saying that is, for instance, that in terms of the sides opposite angle X, so that's going to be BC in triangle ABC, so side BC is opposite side X, and in triangle DEF, side EF is that opposite side. So the ratio of BC to EF will be equal to the ratio of the sides opposite angle Y, so that is going to be AC in the small triangle, DF opposite Y, DF in the larger triangle, sides opposite angle Z, that is going to be AB in the smaller triangle and DE in the larger. And then one thing that College Board seems to be very fond of testing students on is whether students understand that as soon as you determine that similarity, it's not just the sides that are proportional, it is any corresponding lengths. And since the perimeter of one of these similar triangles corresponds to the perimeter of the other, the sum of the sides, or the perimeter, will also follow the same proportion. So if I do BC plus AC plus AB, in other words, the perimeter of the smaller triangle, that perimeter will be proportional to EF plus DF plus DE, the perimeter of the larger triangle. And again, it doesn't matter what length you're talking about, as long as those lengths correspond to each other. For instance, if I drew the midpoint of side AC and the midpoint of side DF, if I drew a segment from point B to that midpoint, and then drew a segment from point E to that midpoint of DF, I still would have the same ratio. This ratio of whatever BC to EF or AC to DF, whatever that ratio is, these two lengths, since they correspond to each other, B corresponds to E, the midpoint of AC corresponds to the midpoint of DF, so these two lengths are corresponding lengths. Those two lengths would follow, so BM to EM would follow the same ratio as all of these other ratios. Let's try an example. In example 6, we are allowed to use the calculator here, so make sure you have your calculator out. Not sure we're going to need it, but we should have it out. So we are told in example 6, in the triangles above, how much longer than segment DE is segment EF. That's what we are asked. So again, let's do how much longer segment DE, segment EF. So how much longer than DE is EF? I crossed off the E there. I don't want to do that. That's dangerous. So here's what we're going to do. First, we're going to see that we've got an X here, a Y here, a Y here. So that third angle, that third angle, I'm going to go ahead and label it Z. It must be equal in both triangles, right? If we had a 50-degree angle here and a, I don't know, 70-degree angle here, we'd have a 50 here and a 70 here, and therefore in both triangles, the last angle would have to be, what's 50 plus 70? So the last angle would have to be a 60-degree angle in both triangles. So again, as long as you know that two angles in two different triangles are equal to each other, the third angle in each of those triangles must also be equal to each other, and therefore you're going to have similar triangles. Here's what I'm going to do. I'm going to set this up very carefully so I don't make any careless mistakes. I'm going to kind of do it the way that we did in this info box up here. I'm going to first write the triangles. I'm going to write, let me do A, B, C. Remember that A is the X angle, B is the Y angle, C is the Z angle. So that triangle ABC is going to be proportional to triangle, what is this going to be? It's going to be D, that's the X angle, E, F. So that's the corresponding vertices. So I know that the ratio of any side to its corresponding side in one triangle and the other, that ratio is going to be constant. What ratio can I establish here? The Z ratio. So in terms of the sides across from Z, I have a 5 in the smaller triangle, the ABC triangle, and then I have a 7 in the larger triangle. So that establishes that the ratio of all lengths in small to big is 5 to 7. They want me to compare DE, DE, and EF. Okay, so DE and EF is here. So in terms of what I need to do, I need to, since EF is across from that X angle, I need to look at the relationship between EF across from the X angle in the larger triangle to BC, which is across from X in the smaller triangle. So here's what I'm going to do. I'm going to set up a proportion. The X angles in the smaller triangle across from the X angle, we have a side of length 7. And in the larger, that's the unknown. That's what I want. That's the EF. So what I'm going to do is I'm going to cross multiply. I'm going to get 5 EF. I'm going to put EF in parentheses just so it's a little separated, equals 49. And that means that EF equals 49 over 5. Now I'm going to go right into the calculator. So segment DE is 7 and segment EF is 49 over 5. They want to know how much longer than 7 is 49 over 5. So I'm just going to do it in my calculator. I'm going to write this over here. 49 over 5 minus 7. Could I find a common denominator here and do this in my head? Sure, I could, but I'm allowed to use the calculator, so I'm going to do it that way to save some brain power. So I'm going to do 49 over 5, and then I'm going to subtract the 7, and I'm going to get 14 over 5. So that is the difference in length, 14 over 5. If I want to convert that to a decimal, I can do so. It's 2.8. So either one of those, if this were, say, a grid-in, either one of those responses would suffice. Is there another way to do this? Yeah, there are other ways to do this. You could use the ratio of two sides in this triangle and compare them to two sides in this triangle. For instance, the way that I could do this is I could use the Z angle and the X angle. So the Z angle in this triangle over here, the side opposite the Z is 5. The side opposite the X is 7. So that's the ratio of the Z side to the X side in this triangle. Well, the ratio of the Z side to the X side in this triangle is going to be 7 to the EF that I want. I'll write EF there again. Well, you can see that is exactly the same ratio as I got over here. So there are other ways to set up these ratios as long as you're putting everything in the right place. So again, what I did here is in the numerators, I put the Z sides, and in the denominators, I put the X sides. And then here I have triangle ABC, both sides there are in triangle ABC. And here I have triangle DEF. So the ratio ends up looking identical to the proportion ends up looking identical to the proportion over here. And of course, when we solve this proportion, we'll get the same exact result as when we solve this proportion. So multiple ways that we can look at these questions sometimes. As long as you're putting everything in the right location, the right spot in the proportion, you should be fine. In example 7, In the figure above, AB is parallel to EC. Okay, AB, EC, they're parallel. AB equals 9. You know what? I'm going to go ahead and label that right now. And the length of AE is twice the length of ED. So they're telling me that this AE is twice ED. Okay, fine. They want the length of segment EC. Before I get started, I just want to point out that the really common mistake that students will make here is because the ratio of this to this, so that is AE to ED, is 2 to 1, students will think, okay, so the ratio is 2 to 1. It's not 2 to 1. The ratio is actually 3 to 1. If there are two, let's call them pieces here, and one piece here, that means the total length of AD is going to be 3 pieces, whereas the length of ED is 1 piece, which means the ratio between, or the ratio of the larger triangle to the smaller triangle is actually a 3 to 1, not a 2 to 1. You got to be careful of that. So now that we've established that the ratio is 1 to 3, we're pretty much done, because we can do this very quickly by just understanding that that 3 to 1 ratio means we just need to divide all of the longer segments by 3 to get the shorter segments. So our answer is 3. But we could set this up with a proportion as well. Again, if we're looking at side, AD to ED, we know there's that 3 to 1 ratio. AD to ED is 3 to 1. And then we could just set that equal to AB, that's the larger. So again, AD is in the larger triangle. AB is in the larger triangle. So that would be AB, which is 9. Let me put that in there, over the EC. And of course, when we cross multiply, we get 3EC equals 9. Divide by 3, and we get EC equals 3. So again, a 3 to 1 ratio means same thing as 9 to 3. 9 to 3 reduces to 3 to 1, and that 9 to 3 follows the same relationship, the same ratio as the one we established initially. In example 8, we are asked for the perimeter of ACD. That's the big triangle here, ACD. So how are we going to do this? First and foremost, we should recognize that we have a 5, 12, 13 here. 5, 12 on the legs. Those Pythagorean integer triples that we reviewed earlier tell us that the hypotenuse of that small triangle must be 13. 5, 12, 13. If you want to use the Pythagorean theorem to determine that 13, that's fine, but it's a time waster, so I would not recommend doing that. Did we even need that 13? I'm not even sure we needed that 13. Yes, we did need that 13. Why did we need that 13? Because the 5 and the 15, by the way, how do we know these are similar triangles? We already talked about this. We know that angle A is equal in both A, B, and E, and A, C, and D. And angle B, we have the 90-degree angle here. Therefore, angle B and angle C must be equal to each other. I did not talk about why these two triangles are similar. We should never really assume that two triangles are similar to each other, but the way that we know these two triangles are similar is the triangles share angle D, and we are told that AB is parallel to EC, which means we know, so again, we can sort of picture this as, so let's say that that's the line that contains AB, and that's the line that contains CE, so maybe like AB is there, and CE is there, and then we have the line that contains AD is sort of a transversal, so we would know that this small angle and this small angle are equal to each other, and that figure on the left corresponds to this figure in that angle A and angle E would be equal to each other as well, and then of course we would know that the third angle, angle C in the small triangle, angle B in the large triangle are equal to each other as well. So again, before you start doing anything with proportions and similarity, obviously you should make sure that you have similar triangles first. You shouldn't just assume. Anyway, back to example 8 here. What is the perimeter of triangle ACD? So what I was about to say is we have similar triangles. We can see that BE, which is the side across from angle A in the small triangle, and CD, which is also the side across from angle A in the large triangle, the ratio is 5 to 15. So that establishes that, again, there's this 1 to 3 relationship in the length, this 1 to 3 proportionality in the lengths, the corresponding lengths of the small triangle to the large triangle. And remember that perimeter follows the same exact pattern. So if my perimeter of the small triangle is 5 plus 12 plus 13, that must be proportional to the perimeter of the larger. So let me do this. I'll do triangle ACD perimeter. P triangle ACD. So what does this, let me write this down here. What does this all come out to? 5 plus 12 plus 13. I don't need the calculator for that. That's 17 plus 13, which is 30 over, I'll just drop the triangle ACD there. I know what I'm solving for. That's going to be cross multiplying P equals 90. And indeed, that's a 1 to 3 relationship, just like the sides showed. So I have determined that the perimeter of ACD, the larger triangle, is going to be 90 by using the established ratio of corresponding lengths, the ratio established by that 5 to 15 relationship. And I know again that the perimeter of the small triangle will have that same proportionality to the perimeter of the larger triangle here. It's also worth noting that in making that calculation, I didn't have to find any of the other segments or side lengths in the larger triangle. I didn't have to find BC or ED or anything like that. I simply used the direct relationship between the perimeter of the smaller and the perimeter of the larger triangle. That is it for similarity.